Okay, today we're talking about polarization. Polarization is just due to the fact that light is a transverse wave. Remember when we studied waves in the past, we talked about longitudinal waves like sound waves in air, where the displacement of the particles was in along the same axis that the energy traveled along. But when we had something like a guitar string, the oscillation, the motion of the string was transverse to the direction that the energy traveled, which is up and down the string. Well, light, as far as we know, is a transverse wave. And because it's a transverse wave, there are two different directions that oscillations can occur and still be transverse to the direction that the light is propagating. For example, if I have a ray of light that's traveling along like this, I could have light that's polarized horizontally, meaning the light is traveling in the direction of the black arrow, and as it propagates, what's oscillating in light? It's an electric and a magnetic field. So imagine that the electric field is oscillating like the red arrow. Alright, so it's a transverse wave. The oscillations, the direction that the electric field is pointing at any given moment in time, is orthogonal to the direction that the light is traveling. But in addition to horizontally polarized light, I could have vertically polarized light, where the electric field goes up and down. Alright, those are both valid transverse waves. You're probably thinking, well, that's not fair for me to just consider horizontally or vertically, because there's a lot of other directions. There's an infinite number of other directions the light could be oscillating at, which would be orthogonal to the direction of the light propagating. But it turns out we only need two polarizations to describe everything. For example, if you look down here, I've got light which is oscillating at 45 degrees relative to horizontal, right? Halfway between horizontal and vertical. You can just think of this little oscillating vector as a sum of a horizontally oscillating vector and a vertically oscillating vector. You add them together and you get this. Alright, so with just two basis polarizations, I can describe all possible other polarizations. So I can describe linearly polarized light pointing in any direction. Alright, this is what we call linearly polarized light, where the electric field is oscillating along a line. It turns out there's other types of polarizations you can get. For example, if I add a little bit of horizontal with a little bit of vertical, but the two are 90 degrees out of phase, when I add them together I get a vector which is going around in circles. This is known as circularly polarized light. So if the horizontal and the vertical components are in phase with each other, I get linearly polarized light. If they're 90 degrees out of phase and they're the same size, I get circularly polarized light. If they're not exactly in phase or 90 degrees out of phase, or if they are not exactly the same size, I can add them together and get a more general state of light known as elliptically polarized light. So an elliptically polarized light sweeps out, the electric field sweeps out an ellipse. Alright? And a circle, of course, is a degenerate ellipse. It's one specific case of an ellipse. A line is also a degenerate case of the ellipse. So the elliptical is the general type of polarization. Now, when we talk about polarization, oftentimes we'll say things like this laser beam is polarized, or the light coming out of this polarizer is polarized, but you might hear someone say light coming from a light bulb is not polarized. What do we mean when we say that light is unpolarized? The electric field's got to be oscillating in some direction. Well, unpolarized light is basically light whose polarization is constantly changing. So in a light bulb or a fluorescent light, all kinds of chaotic stuff is happening. The light's being emitted incoherently. And so the electric field, the way it's oscillating at any given moment in time is rapidly changing. And so that's what we mean when we say unpolarized light, that just kind of something like this, a little electric field vector I'm showing right here. Imagine the light's coming straight at you and you're looking at how the electric field oscillates. It's sort of, right now, it's kind of horizontally polarized, but a moment later it's something else. So unpolarized light is light whose polarization is changing rapidly. Alright, now a linear polarizer is something that will only allow one component of linear polarization to pass. Alright? One example of a linear polarizer is a device called Polaroid. We'll play with some Polaroid sheets in class. Alright? So Polaroid is actually the invention that, if you ever have heard of the company Polaroid that made cameras, is named after this invention. And the way that it works basically is you send in light. So imagine light is going into the page, all right? It's going into the page, and it's polarized like this. So the electric field is oscillating back and forth in this direction. If I get a sheet of Polaroid and put it through my sheet of Polaroid, my Polaroid has one direction that it allows that polarization to pass, and the other polarization gets blocked, all right? So if I send light in with this polarization, what's going to happen is this can be thought of as a little sum of this and some of this. This component gets blocked, this component gets through. So instead of having something oscillate like this, after it goes through my Polaroid, it'll be oscillating like this. All right, so I just keep the component of light which is polarized in the direction that the Polaroid passes the light. All right, so let's imagine, if you will, all right, that I have some light and it's polarized at some angle theta relative to my Polaroid. So imagine, if you will, I've got light polarized like this, but I put in Polaroid that only passes light that's an electric field that's oscillating on this axis, and there's some angle between them. All right? Well, what we're going to do is we're going to write this light as a little bit of the component of light polarized along the direction of my Polaroid passes, plus a component which is orthogonal to that, and we're only going to keep the component that is along the direction of the Polaroid. All right? So if my light were oscillating with an amplitude E0, after going through my Polaroid, I will have light that's no longer oscillating this way. It will be oscillating in the direction that the Polaroid passes light, and the amplitude of that oscillation will now be E0 cosine theta. Now, the electric field is what's oscillating, but what we measure on a photodiode or with our eyes is the intensity of the light, the power per unit area. And it turns out that the intensity is proportional to the electric field squared. We've seen that before in waves. We talked about that earlier, that the amplitude, the power or intensity in a wave is typically proportional to the amplitude squared. So if I have some light with some intensity and I put it in here, right, the intensity goes as the amplitude squared, so what comes out will have an intensity I0 cosine squared theta, and that's where that squared comes from. All right? Now, an interesting experiment which we will do in class, and I'm going to let you think about it now, is imagine I have a piece of Polaroid that only passes light polarized this way. On top of that, I'm going to stack another piece of Polaroid, that only passes light that way. All right? If I shine any light through there, nothing's getting through, right? Because whatever gets through this one won't get through that one. But then I will insert another piece of Polaroid that passes light at 45 degrees. What will happen? I'll let you think about that, and we'll do that demonstration in class. All right? Okay, what happens if I send unpolarized light in? So imagine I send light from a light bulb or from the sun through this piece of Polaroid. Well, what does unpolarized light do? It's constantly changing its polarization, all right? And sometimes it's polarized in the right way, it comes straight through. Sometimes it's polarized in exactly the wrong way and none of it gets through. Sometimes it's polarized at an angle and some of it gets through. All right, but this all happens very quickly. So if you put a photodiode and measure how much is coming through, you'll get a constant value. How much is it? Do you get half of the light coming through? Do you get square root of 2 of the light coming through? What do you get? Well, here's one way to think about it. There's another type of polarizer. Polaroid absorbs the light that it doesn't, that's the wrong polarization. In my lab, we have these little polarizing beam splitters. They're little cubes. They look like little glass cubes. You send light in. One polarization passes through. The other polarization reflects. If you send unpolarized light in, all right, that unpolarized light is going to be this polarization, right? So what actually reflects is usually the polarization that would be in and out of the page, and what transmits. So this is polarization in and out of the page, and what transmits is typically polarization that way, right? Well, my unpolarized light is going to be this as much as it's that. So if I put a photodiode here and measure how much light comes through, and I put a photodiode here and measure how much light comes through, I ought to get equal amounts in both if I send an unpolarized light, right? but I have to conserve energy, so if they're each getting equal amounts, they must be getting half the intensity. So if I send unpolarized light through a linear polarizer, you should lose about half of your light. Well, exactly half of your light. All right, so that's how linear polarizers work. So if I have unpolarized light and I want polarized light, I can put it through a linear polarizer, and it will give me polarized light, but I lose half of my light. It does it by absorbing the wrong polarization. If I have a polarizing beam splitter, if I send in this polarization, it'll all reflect. If I send in this polarization, it'll all transmit. If I send in unpolarized light, I'll get half in each side. If I send some light in diagonally polarized, I'll get some here, and so forth. And the equation that tells me what intensity gets transmitted is that one right there. Okay, another way you can polarize light. So Polaroid works by actually absorbing the wrong polarization. Actually, the way that Polaroid is made is you take plastic that has long polymer molecules, and you heat it up and you stretch it, and you fold it back together and stretch it again, and you do that over and over again till all of your molecules are kind of roughly lined up. And then what happens is electrons can move easily in this direction. So you have an electric field oscillating this way, the electrons move back and forth and absorb it. But light that's moving this way, an electric field oscillating this way, the electrons can't move very well, and so this component of light gets transmitted without being absorbed. All right? So one way to polarize light is by using a selective absorber, like a piece of Polaroid. But I also mentioned there's different ways to make polarizers. And it turns out when you reflect off of a surface, off of a non-conducting surface, it messes with the polarization. All right? So imagine, if you will, I have the surface of a lake, and here comes some light. All right? What happens? Some of that light's going to reflect, and some of it is going to transmit. All right? And the light that transmits, it refracts, right? And we can, theta 1, theta 2, use Snell's law and all of that. All right? Well, it turns out if my light's coming in polarized in and out of the screen, I'll get a different fraction of it reflected than if the light is polarized this way. And in fact, if I send light in at the correct angle, none of this polarization will reflect. All right? And the reason is, you can kind of imagine this. I have light going like this. All right? If I take an electron and I wiggle it up and down like this, it's going to make waves coming out this way, right? But light is a transverse wave, so if the electron's going up and down this way, there will be no light emitted in those directions, right? So you can kind of imagine this reflection right here. It happens because just inside the surface here, the electrons in the medium are being made to wiggle, and then they re-emit this wave coming out here. But if the electrons are wiggling in exactly that direction, they can't emit light that way. There's no component of this oscillation which is transverse to this. All right? So if the angle between the refracted ray and the reflected ray is 90 degrees, this polarization can't reflect. The other polarization can, though. All right? But this polarization will not reflect. So if you go out on the lake and wear polarized sunglasses, you can look at reflections off the lake. There will be a particular direction you can look down at the lake. And you will, with your polarized sunglasses, if you block this polarization, you'll see nothing. You'll be able to actually see into the lake. You'll block the reflection because this polarization gets blocked by your sunglasses, and this polarization doesn't exist because it doesn't reflect at the surface. All right? So the angle at which this polarization transmits 100% is known as Brewster's angle. All right? And how do we find Brewster's angle? Well, if this angle right here is Brewster's angle, this angle down here, theta 2, we know that n1 sine of theta Brewster is equal to n2 sine theta 2, right? That's our law of refraction. That's Snell's law. All right? But in order for this to be Brewster's angle so that we don't get any reflection, all right, these two, the reflected and the refracted beams, have to be at 90 degrees to each other. So this angle right here is theta Brewster, theta 1. Here's theta 2, and that's 90 degrees. So theta Brewster plus 90 degrees plus theta 2 must equal 180 degrees, right? So if I go from here to here, that's 180 degrees. So if this is true, then theta Brewster is really Brewster's angle, and that's the angle we can shoot our beam in at such that we don't get any of this polarization of light reflected. All right, it all gets transmitted. So that tells me then that theta 2 has to equal 90 degrees minus theta Brewster. So we'll plug that into here. N1 sine theta Brewster is equal to N2 sine theta 2, which is 90 degrees, minus theta Brewster. Well, if you imagine, here I am, I'm up at 90 degrees, and then I'm subtracting off theta Brewster, and I'm taking the sine of that, right? This starts, when theta Brewster is 0, this starts at sine of 90 degrees, which is 1, and it gets smaller. And that's kind of like a cosine of something coming up, right? So I'm going to rewrite this. This is N2 cosine theta Brewster. And then if I take sine divided by cosine, I get tangent. So tangent of theta Brewster is equal to N2 over N1. All right? So there's the equation that tells us the angle. We can solve that to find Brewster's angle, and that's the angle where if I shine this light in with this polarization, it'll all get reflected. And that's really handy, right? Because you wear your polarizing sunglasses, and it's going to get rid of the glare off of the lake, right? Because at this particular angle, all of the light reflected from the sun off of the lake or whatever is going to be this polarization, and your glasses block that. But you can still see other things because, you know, light scattering off of the trees and everything around you will have some of the other polarization. Now, what if you're not looking exactly at Brewster's angle? Well, it turns out the amount of light reflected changes gradually. So here's the plot. Here's a plot of the fraction of light that gets reflected for the two different polarizations. All right, and the one polarization you see, it hits Brewster's angle right about here, but it hits it kind of flat. So there's going to be a wide range of angles where you don't get much light reflected from that polarization. So if you wear your polarizing sunglasses fishing, it'll cut out the glare, and you can see into the water and see the fish. If you wear them while you're driving, it'll cut off glare off of a puddle of water on the road or whatever. So that's why polarizing sunglasses are so much fun, because of Brewster's angle. All right? Brewster's angle is also really handy. For example, imagine you're building a laser. So here's a picture of a laser tube. I believe this is a helium neon laser. So there's this gas in here that's glowing. You're trying to get a laser going, and you've got this little mirror here that's reflecting the light back and forth to make the laser. But you've got a window on the end of your tube to keep the gas in. You want to have very little reflection off that window because that can mess up your laser, right? So maybe you go and you think, oh, we know how to put anti-reflective coatings by putting thin films on things. Well, it turns out you can do even better if you just put this glass plate at Brewster's angle. Then, as long as the light has the right polarization, none of it gets reflected off of that surface. You get really good transmission. But what about the other polarization? Well, this turns out to be a bonus because in a laser, the two different polarizations compete with each other, and they can cause all kinds of trouble. But if you give one polarization a tiny advantage, it wipes out the other one. So now one polarization transmits with almost no reflection. The other one gets a little bit of reflection, and that kills it, and your laser's happy. So Brewster windows are a really practical way to get light into a system without getting reflections off of your windows. There are also other ways to affect polarization. There's a property called birefringence. Some crystals have a different index of refraction depending on which way the light is polarized. All right, so some crystals have a structure in them that's not the same in different directions. All right, so you can get, for example, quartz or calcite is a really good one, where one polarization experiences one index of refraction and another polarization experiences a different index of refraction. All right, so birefringence is another way to affect polarization. All right, so you can have they make calcite polarizers where you come into this polarizer at some angle, and how much the light gets refracted by depends on which polarization it is. So the two different polarizations will refract differently, and then you can separate them out and capture one polarization versus another. All right. You can also cut these crystals at normal incidence. All right. So your light coming in, has a different index of refraction for light polarized in and out of the board versus up and down, right? Well, you're not going to refract at the surface because you're at normal incidence, but if you have a different index of refraction, you can give a phase shift to one of the polarizations relative to the other. So if you send in light polarized like at 45 degrees, so it's a little bit of this and a little bit of this, you can induce a phase shift between the two. And that's actually how we make circularly polarized light in my lab. We start with a linearly polarized light, right? And our light's polarized this way, kind of, our light's coming in here, but now looking if the light's propagating into the page and we hit our crystal, right? We can think of light polarized this way as a little bit of light polarized this way plus a little bit of light polarized this way, and our calcite crystal will give us a phase shift between the two so that we can turn our linearly polarized light into circularly polarized light. You can also get polarization by scattering, right? I mentioned when we take something and we take a charged particle and we wiggle it. If we wiggle it this way, it'll make waves coming out like this in all different directions, but not straight up and down. You get what's known as a dipole emission pattern. That kind of, you look at how much light is emitted in different directions. You'll get a lot of, if you wiggle it up and down like this, you'll get a lot of light scattered in those directions, no light scattered in those directions, and a little bit of light scattered, you know, in those directions. All right? So imagine, if you will, we're standing here on the Earth, and here's the sun shining at us. The sun is unpolarized. So if we look up at the sun, don't look straight at the sun, but if you did look right up at the sun with a polarizer, you'd get about half the light through. It's just unpolarized, all right? And if we look at the sky near the sun, right, so here we have the light coming from the sun, it's unpolarized. So I've got some waves going this way and some waves going in and out of the board, all right? So if I wiggle an atom, you know, this way, right, if I look up in the sky, the stuff that's wiggling this way is going to make a little bit of light towards me, but stuff that's wiggling in and out of the board is going to scatter a lot more light. And if I look up at exactly 90 degrees from the sun, I'm going to have, so I look up in the sky, the sun's over here, I look at 90 degrees from the sun, so this is, I didn't draw this very well, but if I look at a 90-degree angle, some of the sunlight will be doing this, and some will be going in and out of the board. The light going in and out of the board can scatter in this direction, but the light that's oscillating this way cannot scatter and go in that direction, right? If it's wiggling that way, it can go in every direction except these two. So if you take your polarizing sunglasses and you look at 90 degrees to the sun and rotate them around, you can make the sky very dark because only one polarization component is scattering towards you at that particular direction in the sky. If you look not at 90 degrees from the sun, then you get a little bit of both. There's also something called optical activity, which can affect polarization. One good example of that is sugar. Sugar molecules have a definite helicity. They only rotate one direction. They kind of make a helical shape, and they only form with one-handedness. I believe it's left-handed, but I can't say for sure. So if you put a bunch of sugar molecules in water, dissolve them, and you send your light through, you can kind of imagine this sugar molecule, electrons can move up and down here, but they can't move that way. Here electrons can move like this, but they can't move that way. So it's almost like you have a stack of polarizers that pass light this way, 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 this way. And what you can do is actually get the light to rotate its polarization. So if you have sugar water, and I've tried this, it takes a lot of sugar to really see this effect. Best thing to try, Caro syrup. Put Caro syrup in a bottle, shine polarized light through it, the polarization will rotate, and the further it goes through it, the more it will rotate. All right? And anyway, that's polarization. I'm going to show you quickly a fun thing you can do. I mentioned birefringence. Birefringence shows up in all kinds of things. In a calcite crystal, it's just the structure of the crystal. If you look like at a glass window, glass is amorphous. It shouldn't be birefringent, but there are stresses in the glass that kind of make it locally birefringent. So if you take a plate of glass, the index of refraction at any given point will be different for two different polarizations of light, but that changes throughout the glass. So one thing one of my students noticed and came up to me and said, Dr. Durfee, when I walk out of the Eyring Science Center and I look at the glass, I see like this weird checkerboardy, blurry pattern. And that's because he was looking, the time that he came out of class, the sky behind the door was at 90 degrees from the sun, so the light scattering in the sky was polarized. And his glasses would block a particular polarization. But then the glass in the door was birefringent, and it would rotate and change the polarization of the light it went through, but different parts of glass did it differently, so he saw patterns in the glass. That's a really fun thing to try. You should do that. Anyway, how do 3D movies work? Why do I bring this up? This is kind of off on a tangent. Doesn't really have to do with the class, but I know you're interested because 3D movies use polarization. All right, so the idea is the main way that your brain determines how far away something is something called parallax. If there's something right here, and here are your two eyeballs, all right, you have to kind of cross your eyes to see it. If it's further away, you don't have to cross your eyes as much. All right, so your two eyes see two different images, and they kind of put them together and figure out what that angle is. And that tells you how far something away is. So in a 3D movie, the idea is you're going to feed your eye two different images. So in one image, the image for the left eye, you put a ball right here, all right? For the image for the right eye, you put the picture of the ball right here, and then it looks like the ball is out there, all right? So how do I feed two different images to my eyes? Well, what they do is they have two projectors, all right? One projector projects one polarization of light, one projector projects the other polarization of light, and then you have your glasses that are polarizers, so that the image that's polarized for your left eye only gets through this polarizer, but it doesn't get through this one, and your right eye doesn't see it. The image you project for your right eye has the opposite polarization. It gets through this polarizer, doesn't get through this one. All right. In the old days, they used red and blue filters. They used different colors to block for the two eyes, but that distorted the color of your film. That was no good. All right. And so eventually they switched to linear polarizers, where one polarizer would maybe be polarized to let this light through and one polarized to let this light through. Then there was the problem that if people tilted their head even a tiny bit, things got kind of blurry. And so nowadays they actually don't use linear polarizers, they use circular polarizers, where one eye sees the left-hand polarized circular light and the other eye sees the right-hand polarized circular light. All right, so that's how 3D movies work. It's sort of separate from the things we've studied in this class, but the fact that they use polarizers is kind of cool. All right, I actually have a pair of 3D glasses they use at the theater. We use them to align our optics down in my lab because we need a couple laser beams that are left-hand circularly polarized and one that's right-hand circularly polarized, and I've got a left and right-hand circular polarizer in these glasses. Pretty cool. But it turns out there's other things that your brain uses to try and figure out depth. So the 3D movies we see aren't perfect because your brain is also looking at how your eye has to focus on things. Now, this is the dominant one, and so the movies still look 3D, even though your individual eyeballs are focusing on the screen. Your brain still thinks the thing's back there. In a hologram, you really make an image. You make an image that really reproduces the wavefronts coming from an object. So your eyeball has to focus where you see the image as well. So a hologram looks more realistic than a 3D movie. If we could do holographic movies, that would be really cool. But 3D movies take advantage of the fact that your brain does not weigh the focusing of your eyeball as much as it weighs the parallax between your two eyeballs when it determines depth. All right? But also context can be used to determine dimensionality. Kind of, your brain interprets things based on the image as a whole, what things are surrounding different things. And as you'll recall, I mentioned that oftentimes in real life, a lens will make a real image. We'll have some object here, and it'll make an image over here, and you look at it with your eye, and it should look like it's floating in front of the lens, but your brain says, typically the lens is small, the scene is big, and your brain says, look, this object here, I only see this object when I'm looking through the lens. If I look down in this direction, I don't see the image, right? Because the image only occurs when the light bends from the lens to my eye. And so even though you have a real image floating out in space, your eye says, no, it really must be behind the lens because I have to look through the lens to see it, right? So your brain uses the context to try and determine where something is. And that's why it's hard to see real images. You need a big optic so that you can see the whole image without getting past the edge of your lens or your mirror. All right? So your brain is fooled into thinking the image forms back here, even though if you put a piece of paper out and see where it focuses, you see the image forms right there. But you can use context intentionally to trick your brain into thinking something is a different place than it is. And I'm going to show you a little video I made of a bouncing ball. The bouncing ball all happens on the screen of your computer, right? There is nothing inside or out of the screen. All the pixels are on your screen. But if you're lucky, your brain will trick you into seeing something a little different. Here we go. Do you see that? So your brain sees these lines here, and it's thinking that's part of the frame. The ball must be behind the frame. If the ball comes past the frame, it must be coming out of the screen. I think that's pretty cool. So context also matters.